Hey everybody, my name is Emmanuel with Computer Architecture. This is my Arduino project, my presentation for CSIS 2810. So I decided to build a 3D rasterizer. It is the graphics algorithm that draws three-dimensional images. I've always wanted to do this, and it's taken me a very long time, but I finally found the perfect opportunity, and I'm glad that we were able to do this project. So this is the paper that I wrote that explains how it works. There are 16 pins that are run from the Arduino processor to control it, and then there's 2 additional wires that are run from a power supply to the to the LED matrix to give it power. I give it 2 amps of power at 5 volts. The graphics are relatively simple. Here I give a basic explanation of how we draw a 3D cube on a 2-dimensional surface. What we do first is draw a square, and then we're going to pretend that the back side of the cube is twice as far away as the front side, so consequently it is half the size on the screen, which makes the calculations fairly straightforward. Then we connect the 2 squares together using edge lines, connecting the various corners of each square to one another, and we have completely drawn a 3D cube on the screen. Now, to use this math to draw 3D images efficiently, we need to generate formulas that spit out the values, the x and y values on the screen for the 3-dimensional coordinates of the cube's vertices. So here is where I explain how that is done. So if we take a screen that is 32 pixels by 32 pixels, I guess we don't really care about how many pixels it is at the moment. What we're going to care about here is that the left side of this graph has an x value of -1. The right side has a value of +1. The bottom has a y value of -1, and the top has a y value of +1. So putting the upper right corner of the cube from the face side, the near side of the cube, on the screen, it's going to transpose to right here. Excuse me. Sorry about that. And the way that I got this coordinate here is we're going to assign our first vertex of the cube at the 3D coordinate of 1, 1, -2. So that is 1 unit to the right, 1 unit up, and 2 units into the screen. So the algorithm that converts these 3 coordinates here into screen coordinates of 0.5, 0.5 is that we take the x value of the x 3D value, that is, and then we divide it by the negative z value so that we get a positive number, because z is negative to start with. And that takes this 1 here, and when we divide it by a -2, we get, when we divide it by a -2, we get a positive 0.5 for the x value. The y value is exactly the same. We divide it by the -z, since z is negative to start with. 1 divided by -2 is also 0.5. So just like the previous image, where we draw an object that's twice as far away is half the size on the screen, we are simply dividing by the distance away, which is where we come up with this formula. The 3D coordinate is the 2D coordinate. The 2D coordinate is the 3D coordinate divided by the z depth. So anyway, if we repeat that pattern, we can draw the next 3 vertices of the front side of the cube. These are their 3D coordinates, which then convert into these 2-dimensional coordinates here. giving us this image right here. Then if we take and plot 4 more points, and instead of at a depth of -2, we're going to plot them at -4, so they're twice as far away, they will take up half the size on the screen, and using the formula, we get values of 0.25 plus or minus. And so here are the first 4 coordinates of the front side face, and here are the back 4 coordinates, the back 4 vertices at their various coordinates. So, like I said again, this inner square here is exactly half the width and height of this front side square because it is twice as far away. And then to finish the cube, we just connect the vertices using a simple connect the dots algorithm and a line drawing algorithm. Now, obviously, this is just a square object. If we want to rotate this in 3-dimensional space, then we have to know a little bit of trigonometry. So this is a graphic that I got from a web page that gave me a straightforward formula that rotates x and y coordinates in a 2-dimensional plane. These are the formulas. You just take your x and y values and you plug x and y in, and you get an x out. We could call this x translate and y translate. This gives you the new x and y values after you rotate it theta degrees. Here's a table of the original 3D coordinates and the new 3D coordinates that we get after we apply that algorithm, that formula. So with the new rotated coordinates, we want to convert those 3D coordinates into 2-dimensional screen coordinates like before, using the same formulas as before. X2D equals X3D divided by -Z3D, and the same with the Y coordinate as well. Here is the result of rotating the cube approximately 30 degrees counterclockwise, which is what happens when you use the formula. All of these coordinates here are these 8 coordinates of the black cube that we see on the screen here. Now, this obviously is only rotating around the z-axis, and none of the points change distance from the screen. And so if we want to rotate it on a different axis, we just have to modify the variables of the equation a little bit. Here's the original equations. So this rotates around the z-axis. Notice how the z-axis is not included in the formula. If we want to rotate around the z-axis, then if we want to rotate around the y-axis, then the y-axis has to be the variable that is not included in the formula. So here I've replaced the y values, or the y variables, with z variables. So now y is the variable that is missing from both of these equations, and I just have x's and z's. This means we're going to be rotating around the y-axis. Now, like it says here, if we want to truly rotate this around the y-axis, we do want to bring the cube temporarily into the origin of 3D space, then perform our rotation, and then move it back, which is fairly simple. It's just addition. We move it 3 units because the center of the cube is 3 units away from the viewpoint. Now, when we take a cube and we want to fill in some of the faces, like on the cube that I've designed, I'm going to fill in the top face and the bottom face. They're squares. So I take and draw a line between 2 corners to divide each of those squares up into triangles. It doesn't look very much like a triangle there, but it's a triangle. This is side 1, 2, and 3, and then this is also a triangle 1, 2, 3. Did the same thing with the bottom square. And the reason we do this is because a triangle is the simplest polygon that can be defined in a three-dimensional space. And so in 3D graphics, it is the convention to draw all three-dimensional objects with 3D with three-sided polygons, triangles. So then I went ahead and used a simple algorithm to fill in that triangle with color. I filled in all 4 of these triangles. And of course, these black lines should not be seen in the final product. So in the next scene here, I just erase those just to show that all we did is drew the squares. Now, because I don't have enough memory in an Arduino processor to store depth information for every pixel, which is the distance away from the viewpoint, usually you would use that data to determine which pixels are drawn in front of which pixels, which objects are in front of which. But since I didn't have that advantage, I had to kind of cheat to get the correct depth information, and I just drew the 2 squares and then drew the lines in front of everything so that when these lines are drawn in front of the square, they're drawn on top of it instead of behind it. Now, because the Arduino processor is limited on its RAM, it only has 2K of actual local variable RAM, and it has 32K of instruction RAM. I had to convert some of my arrays into functions. So here's an array that stores 24 values, and it did not let me store this array. It's too long. It wouldn't handle it. I don't know why exactly. I know there's enough RAM for it, but it seemed like it ran into problems when I tried to use this array. So I converted it into this function here, which spits out the exact value for every one of these points. And these are actually the XYZ coordinates of the cube that I am using. These coordinates are a little bit different from what is in the demonstration above this, but this made the calculations easier for me and simpler to manage. So I have a cube that is essentially all of its corners are 0.5 units to the positive, negative, x, y, and z directions. So this coordinate here is at negative 0.5, negative 0.5, negative 0.5. And then a cube has 8 vertices. That's why we have 8 different lines. 3 values per line because there's 3 dimensions to the location of every vertex. And here is the formula, of course, that I use to spit out these same values and alternate the positive and negative signs accordingly. There were some other arrays that I was also unable to store in the Arduino's memory. And so instead, I took this array here and I made a switch case structure. It used up instruction memory instead of the local variable memory, and there's a lot more instruction memory. So even though this is less efficient, there's a lot more memory that's available to store it this way. And at last here, I used this method here called matrix.drawPixel. This actually comes with a library of functions that came with my 32 by 32 LED matrix, and I plug in an X and Y for a column and row, and then I use hue, saturation, and value to define colors. This is the hue. I'm not sure why that's a 3, but anyway, it spits out the correct value in the program. The saturation and value. I'm not sure what the true value is. The true value here is for, but I just feed it a true because that's how it came in the demo. And then after everything is set up, this is the final product. This is the picture that it drew, and then to show you that it can do proper depth for the pixels, here is an image where the cube is slightly rotated, and this beam here is drawn in front of the red square that is behind it. Now, again, I cheated to get this blue line to appear in front of the red squares by drawing the red squares first and then drawing the blue line on top of it. So I have the device connected to my Arduino processor right now. I've connected a 2 amp 5 volt power supply. It can go up to 15 volts. This is specifically made for 5 volts. And then here is the 32 by 32 LED matrix. It is currently running the cube, rotating it slowly. Since I didn't have enough RAM to store the pixel data for the image, for whatever reason, I wasn't able to render this the way you would normally. Normally you would just see the image get replaced immediately with another image slightly rotated, with the cube slightly rotated. But in this case, I have to erase the cube so that I can draw the next frame. And so you see the erasing happen because I'm not able to hide that information in an array. It has to be seen. Basically, the only way I can store that information is in the pixels themselves. But anyway, this is it. I've wanted to do this for a long time. It was very exciting, and I was very glad to be able to carry this out. Earlier, I did work on a different project. This wasn't going to be my Arduino project. I was actually going to build a matrix that projected light through a Fresnel lens like a projector onto a 3D spiral to make a spiral hologram. And I ended up making the LED matrix. It's actually right here. It's a 24 by 24, and I would connect 3 Arduino processors to it, and it has 24 rows and 24 columns. I would connect 24 of the, I would connect 8 of the rows and 8 of the columns to a single Arduino processor, and then I would use 3 processors to get all 24 rows and all 24 lines connected. This works, and it actually spits out a frame rate of about 2660 approximately, which is insane, but it was good enough. I needed a high frame rate if I was going to run the 3D hologram that I wanted to run. Anyway, this is going to be the end of my video. I hope you guys all enjoyed this, and I hope you have a great day.